Hello there, I'm Christopher Morrow from the University of Edinburgh. I'd like to tell you about our work on skill-based shared control. Industrial tasks rely on operators to perform specific motion patterns that achieve different goals. This results in expensive and time-consuming training. We see similar cases in other applications. In welding, they employ various weave patterns, and you can see here the patterns being repeated around a central path. And also, similar patterns are utilised in plastering. I'll refer to these patterns as skills. We assume a standard teleoperations setup, and that the operator has an inherent description of the skill that they're trying to reproduce, but our only observation of this is via the interface. So the focus of this work was to develop a shared control framework that assists an operator to maintain a skill, whilst ensuring environment constraints. We summarise this problem in three parts. The first, skill assistance requires some encoding of a number of skills. Second, the type of interaction should be seamless. That is, the operator should not be given the additional burden of specifying the skill to the system. Rather, their intention should be recognized from the interface signals. And third, this encoding should be versatile enough to adapt the motion for obstacles whilst respecting the skill. For example, the wave's amplitude and wave frequency. Key to our model is the distinction between the state and underlying trajectories and a skill model. Combining their parameterizations results in an encoding theta describing the state found by this functional. Controls are taken as the derivative of states. We use a particular model that allows us to specify a number of skills. In our experiments, we present results for the wave and cycloid skills. For the underlying trajectory, we use a geometrical primitive called Clothides. These have been utilized in road design, autonomous driving, and continuum robotics. In our case, Clothides give us a versatile and compact representation. Direct control maps joystick commands onto robot motions. Our proposed shared control framework tracks a window of interface signals and uses these to estimate the model parameters that describe the operator's intention. We search within the parameter space by solving a nonlinear regression optimization. We assume there may be a set of skills available to the operator, each with a given parameterized model, and we perform a model comparison to classify the operator's intention. The estimated intention is passed to a trajectory optimization step, which, subject to constraints, optimizes a convex cost function offset by the estimated intention. This preserves the principle of minimal intervention, which is important for the user's acceptance of shared control systems. We are able to find solutions fast enough to facilitate an MPC loop. This allows us to adapt signals to changes in the environment and operator intention. We have evaluated our method by conducting 4 experiments. The first highlights the method's ability to adapt to changes in the operator's intention. We detect a change of intention by comparing the costs of a number of skills and choose the best fitting model, as shown in the video. Next, we look at a static obstacle avoidance experiment. We recorded interface signals under direct control, where the operator inadvertently leads the robot into constraint violation. When played back under shared control, the motion adapts to the constraint whilst maintaining the skill. Next, we look at a dynamic obstacle experiment. Due to the MPC nature of the method, by tracking obstacles and representing them as parameterized constraints, we are able to adapt signals to dynamic changes in the environment. We also performed a user study with several participants to further validate our method. This study indicated that participants' performance improved for complex skills and was maintained for simpler skills. Based on our observation, we hypothesized that our method leads to lower cognitive loads, which we plan to investigate in future work. In addition, by mapping commands into 3 dimensions, we can apply our methods to non-flat surfaces, making it more applicable to realistic industrial applications. To summarize, we have proposed a model-based shared control framework. We have introduced Clothides as a novel representation for our purposes, and implemented our method within an MPC loop, and validated our framework's capabilities. Thank you for listening.